Okay, let's continue to the next part of the lecture, which is out-of-order execution. We're going to make some headway into it, and then we're going to continue this next week. And clearly, this is a very exciting concept that has really, in my opinion, revolutionized how processors were designed starting with 1990s, mid-1990s, when Intel Pentium Pro was introduced, which was the first general purpose commercial out-of-order execution machine. It actually had a breakthrough change in performance. And we will see that concept in a little bit. But this is to remind that these are the readings that we're going to follow. There's an optional reading that I put, which is an example of a real microprocessor that implements out-of-order execution. And the week after that, we're going to, well, next week, we're also going to start branch prediction, which is going to be important, very important for out-of-order execution. There's a reading that I assign over here, which is an important reading. So basically now we're finally going into out-of-order execution, and then later we're going to talk about other execution paradigms after we finish issues with out-of-order execution as well. And this is the last slide. I'm not going to go through this in detail, but essentially with precise exceptions, this is the pipeline we have built. We have an in-order pipeline where decoding and writing to the reorder buffer happens in order, dispatching of instructions happens in order, in program order, and instruction can be dispatched into the execution units only if its results, its source registers are available, basically, essentially, right? It needs to have its operands available somehow. If it's not available, then it stalls the decode stage. In the middle, things can execute out of order, but that's not the same thing as out of order dispatch, as we will see, which we're going to enable now. And later at the end of the pipeline, when instruction finishes, it starts its result into the reorder buffer. And then when the instruction becomes the oldest instruction that doesn't have an exception, it writes its result into the register file. And this way we handle true dependencies nicely. We eliminate anti and output dependencies through renaming. And this is going to be essential to out-of-order execution. And we just covered the slide, so I'm not going to repeat this again at this point. So basically, let's take a look at out-of-order execution. This is also called dynamic instruction scheduling. Essentially, hardware is going to schedule instructions in an order that's different from the one that's specified by the programmer, essentially, or the compiler, right? In an order that's different from the von Neumann model order, let's say. So this is our in-order pipeline again, simplified. I just removed the reorder buffer access over here, which is part of the decode stage now. But basically, the problem is with dispatch. Essentially, when we're dispatching, we're really sending an instruction to a functional unit after it's decoded. And renaming with reorder buffer eliminates stalls due to false dependencies. But if you have a true dependency, true data dependency, the dispatch of the younger instructions into functional units stalled, actually the younger instruction in the pipeline. If this instruction, the decode stage, is dependent on an earlier instruction that has not produced its result yet, this instruction has to stall, right? And that's a problem. That's the problem with the pipeline that we have seen, even if you add a reorder buffer into it, right? Okay, the question is, can we do better? Basically, as always, we've asked this question: can we do better? Now we're going to try to overcome this dispatch stall. Basically, the question is, of course, how can we do better? But before we get into it, let's take a look at what's happening. Basically, these are two different pieces of code. As you can see, the first instruction, imul or integer multiply or load, is writing to register 3, and the next instruction is reading from register 3. And all other instructions, the blue ones over here, are independent. But the problem is this add instruction needs to wait until the multiply produces its result so that the later instructions can go into the pipeline and can execute. Even though the blue instructions are independent, they cannot go into the pipeline because the add instruction stalled in the decode stage, right? Now, this multiply may be only 4 cycles or 8 cycles. So that's an 8-cycle stall. But look at the case on the right. This add instruction may need to wait 500 cycles, or in the case of Xbox 360, as I mentioned, 650 cycles, potentially, if this load takes 650 cycles to execute, right? So basically, these two, in both of these codes, the add instruction has to stall, and the independent instructions cannot enter the pipeline until the add instruction goes into the pipeline, as you can see. But the blue ones are actually independent. We should be able to have a way to execute them, basically, without waiting for the add instruction and the multiply instruction or the load instruction in the second case on the right over here. So basically, the problem is first add stalls the whole pipeline. Add cannot dispatch because its source registers, in particular, its source register R3 in this case, not necessarily R1, is unavailable. And as a result, later independent instructions cannot get into the pipeline. And as a result, they cannot be executed, even though they're completely independent. So there's a difference between the two code portions also over here. And that's the difference between a load and a multiply. So basically, load latency can be completely variable, unknown until runtime, right? Multiply latency can also be variable, as we discussed last time, but maybe it doesn't vary as much. So maybe multiply is not the best example over here. It could have been an add, another add over here, FP add, for example. But basically, load latency is very much variable depending on where the load gets serviced from in the memory hierarchy. And the compiler may not know this information very well. Basically, the scheduling of the code at compile time is very difficult in this case, especially if this load takes 600 cycles sometimes, right? Multiply is not going to take 600 cycles. It may take 8 cycles, let's say, but load is going to take 600 cycles. How do you schedule the code at compile time to cover for that is difficult, basically. So as we discussed last time, compiler versus microarchitecture-based scheduling, actually out-of-order execution is going to be even more powerful when the latencies of instructions are variable, because the compiler cannot do a good job scheduling instructions in those cases. And the latencies of instructions are long because, again, compiler cannot do a good job in those cases because it needs to fill the pipeline bubbles, if you will, with 600 or so instructions, which is not easy to do. So, okay, how do we prevent dispatch stalls? Basically, the problem we identified with the in-order processor is it's in-order dispatch. This is also called scheduling. We are scheduling instructions in order, in program order, into the execution units. It's also called in-order execution. But I like the term in-order dispatch because it's very specific, right? You're dispatching the instruction from the decode stage into the functional unit, and you're doing it in program order. So solution is basically very simple, conceptually, again, out-of-order dispatch, or out-of-order scheduling, out-of-order execution, or dynamic scheduling. Actually, we have seen the basic idea before. Basically, the data flow machine fires an instruction only when its inputs are ready, right? We will use similar principles to data flow, but we're not going to expose in the ISA. We're still going to keep the von Neumann model in the instruction set architecture, but underneath, we're going to use data flow principles. Okay, before we go into dynamic scheduling a little bit more, let me ask the question, any other way to prevent dispatch stalls? And we have actually discussed this earlier in the earlier lecture, last lecture. We could do compile time, instruction scheduling, and reordering, but this may not work well, as we discussed. This is actually very difficult if you have very long latencies and variable latency operations. Value prediction, this is another potential solution, but this complicates the pipeline, as we discussed, right? You predict the value you're dependent on, even though the value may not be available. And also, if you mispredict, then you have a problem. Prediction accuracy needs to be reasonably good for this to work, and reasonably good prediction accuracy is hard to achieve. Fine-grained multi-threading is another approach. Clearly, this prevents dispatch stalls. You don't stall at all, right, as long as you have threads. But the problem is this doesn't help you. This doesn't help you with single thread performance. As we discussed, this helps you with throughput, but single thread performance suffers in this case. Okay, somebody says fill the bubbles with independent instructions. That's essentially, yes, what we said with compile time, instruction scheduling, and reordering. Okay, so the basic idea of out-of-order execution or dynamic scheduling is to move the dependent instructions out of the way of independent ones, such that independent ones can execute. It's a very simple idea. You're basically providing some area, hardware area, where you buffer the dependent instructions. And we will see that actually everything is buffered in that buffer. These are going to be called reservation stations. And this buffer enables you to execute instructions that are ready, whose input values or operands are ready. And instructions that are dependent on other ones wait until their operands become ready. It's a beautiful idea. It's a very simple idea. It's a data flow idea, basically, as we discussed. Basically, you can think of this as rest areas for dependent instructions. These are also called reservation stations for historical reasons. I'm sure many of you drive cars, right? If you think about a road, if you're in a single lane, some cars may be slower than you, right? You may be dependent on that car. Let's assume that slowness. And everybody is limited. Your throughput is limited by how slow that car is. And if some car stops in front of you, for whatever reason, it may be dependent on something, right? You have to stop also. But this is not reasonable, right? Nobody would be happy if some car arbitrarily stops in front of you. Of course, there could be exceptional conditions, the car breaks down. But for other reasons, if some other car stops in front of you, the entire pipeline of the road gets stalled, right? So what do? You move the car out of the way. It goes to a rest area. It goes to an emergency lane so that it deals with whatever it needs to deal with over there. And if all cars that have some dependency on some condition move out of the way a little bit, then the pipeline keeps flowing such that independent instructions that do not depend on that condition can continue executing. Yeah, this analogy is nice. I think it's not a perfect analogy, of course, because cars have don't necessarily have dependencies like instructions do, but it's the same concept. You move the dependent instructions to some special area in hardware called reservation stations. And while the instructions are in the reservation stations, we add hardware to monitor the source values of each instruction in this resting area called reservation stations. So there's some additional hardware we need to add to capture the values. When all source values of an instruction are available, and we need to detect this, of course, and we will see how we detect this in the next lecture, we can fire or dispatch the instruction into the execution unit because we know that the values are available at that point. Instructions are now dispatched in data flow and not control flow order, right? So the benefit is latency tolerance. This allows independent instructions to execute and complete in the presence of a long latency operation, as you will see. So let me give you this picture over here. Basically, this is the picture with an in-order dispatch and precise exceptions. And this is the code that I showed you earlier. I changed it a little bit. You can see that this add is dependent on the multiply. That's why it stalls. Yeah, and this add is also stalling over here, as you can see. And as you can see, this is an in-order pipeline. So the independent instructions also need to stall. So this blue instructions, even though they're independent, they stall. So as a result, this takes 16 cycles. But if you look at out-of-order dispatch, what happens is, and we are maintaining precise exception in this case, we move the instructions into a waiting area if they're supposed to stall. Instead of stalling, they're waiting in the reservation stations. So later instructions can get decoded and executed because their values are available. So these two independent instructions can basically flow through the pipeline, decoded, executed, and only the instructions that have to wait for data values actually wait in this case. So you can see that if you enable something like this, you can reduce the 16 cycles to 12 cycles, which is a significant improvement. That's 25% performance improvement in this particular case, assuming you don't change the clock cycle time, of course, right? And in real machines, actually, the benefit you get out of out-of-order execution is much higher compared to in-order execution because this is a very simple piece of code. In real machines, you actually have many, many more stalls and longer latencies, variable latencies, etc. Okay, so how do we enable out-of-order execution? I will cover the fundamentals and then stop. But basically, there are four things. There are four things that you need to have. First of all, you need to link the consumer of a value to the producer, and we know how to do that. Remember the renaming, register renaming? We're going to use that. Then you need to buffer the instructions until they're ready to execute, and we know how to do that with reservation stations. You need to provide this resting areas, as we will see later. Instructions need to keep track of the readiness of their source values. There needs to be some hardware to do that. And we kind of saw this, but we're going to see it exactly right now. When all source values of an instruction are ready, you need to dispatch the instruction to its functional unit. So this is going to be also, you need to monitor this also. Okay, so how do we enable these four key concepts in out-of-order execution? Linking of the consumer of a value to the producer is done via register renaming. You associate a tag with each data value to be produced into a register. It could be the reorder buffer ID, this tag. It could be something else, as we will see also. It could be the reservation station NPID. It could be some arbitrary namespace, as long as you provide this linkage. Why do you buffer the instruction until they're ready to execute? You insert the instruction into reservation stations after you rename the instructions. Okay. How do you keep track of the readiness of the source values of an instruction? Whenever an instruction produces a value, it broadcasts the tag and the value. And instructions that are waiting for that tag compare their source tags to the broadcast tag. If there's a match, then the source value becomes ready. Remember, we linked the instructions using a tag. Any instruction that's waiting for a value knows the tag of the value. And any instruction that's going to produce that value knows the tag of the value. When an instruction produces the value, meaning makes its result available or finishes its execution, it broadcasts that tag to all places in the machine where instructions may be waiting. And any instruction that's waiting for that tag compares the tag and sees that the tags match. And as a result, it captures the value that's also broadcast, essentially. So it's going to be complicated. As you can see, we're going to add comparators to enable this, but it's going to be a very powerful idea that's going to enable the broadcasting of the value to other instructions that are waiting for the value. And when the instruction actually captures the value, then the source value becomes ready. When all of the sources of an instruction become ready, the instruction wakes up. This is called wake up, meaning that it's ready to be dispatched. If multiple instructions are awake at the same time, and if you don't have enough functional units of the type that you need to execute the instruction on, you need to select one of the instructions per the functional unit. So you need to have some arbitration logic. But we will see these are real conditions. Clearly, you need to have that sort of arbitration logic. So this out-of-order execution, as we discussed with register renaming, is invented by Robert Tomasulo in the 1960s, actually. Oh, sorry. It's used in IBM 36091 floating point units. The problem was, this is a beautiful machine, and I would recommend reading this paper, actually. If you take my seminar course, we sometimes read this paper or similar papers related to IBM 36091. But basically, this idea did not take off at the time. Why? Because this machine did not have precise exceptions. So it did auto-order execution, but it did not maintain the state like we discussed earlier. As a result, it was terrible or almost impossible to debug. In fact, to produce this machine, there was a lot of discussion within IBM. Should we really produce it? Should we not produce it? And in the end, they decided to produce it. And it was great that they produced it, but commercially, this was not a success because it was impossible to program, because it was reordering instructions in an out-of-order manner, as we discussed. But it was not providing the precise exception semantics to the programmer. So it was breaking the IBM 360 ISA, instruction set architecture, actually. And as a result, it did not get adopted. What happened today, and what happened 18 years later, is people figured out how to incorporate out-of-order execution and precise exception principles together. And then out-of-order execution really took off. And that was actually provided by these two works that was published in 1985. It's called the High Performance Substrate, that introduces the idea of precise exceptions and out-of-order execution at the same time. Intel Pentium Pro, which was the first really commercially successful out-of-order execution machine, incorporated both a lot of principles from these works and incorporated both out-of-order execution and precise exceptions. And later on, out-of-order execution variants are used in most high-performance processors today, initially in Intel Pentium Pro and later AMD K5. But today, almost all high-performance processors use out-of-order execution, including Apple's M1 that I added over here. But essentially, the way out-of-order execution is done in today's processors looks like this. You fetch and decode. After you decode the instruction, you put into the reservation stations in order, in program order, after you rename the instruction. Now, in the scheduler, things happen in a data flow order, basically. Whenever instructions execute, they broadcast their tags and values. And any instructions that are waiting for that tag capture the value. And whenever the values of an instruction are available, they can get dispatched into the functional units. So basically, execution in the schedule part completely happens in data flow order, which means out of order, data-driven manner. Whenever the data values of an instruction are available, the instruction can get dispatched. After the instruction finishes, it writes its result into the reorder buffer as well, in addition to tag broadcasting its tag and value. We will see that later on. And then you reorder the instructions just like we discussed earlier in precise exceptions, right? Basically, you write to the register file and memory in program order. So basically, you have a machine with two humps. One is the data flow scheduler over here, and the other is the reorder buffer at the end. And anything before the data flow scheduler is in program order. Anything in between the scheduler and the reorder buffer is out of program order in a data flow order. And anything after the reorder buffer is in program order, which means committing to the architectural state is completely in program order, basically. Okay, somebody asked, how do you remember the initial program order if you execute out of order? Well, you write to the reorder buffer, right? You write to the reorder buffer when you decode in program order. So nothing has changed based on the previous discussion we had. Whenever you allocate an entry in the reorder buffer, that happens in the program order. So reorder buffer contains a list of instructions in the program order. Okay, good. Okay, so basically, there are two humps here. One is the reservation stations, which is the scheduling window. And the second is the reorder buffer. In other words, instruction window or active window, which has the list of all instructions in the machine that are decoded but not yet committed. Scheduling window may have instructions that are not executed yet, but they're decoded. But it doesn't have the instructions that are executed but not yet retired, essentially. So I liken this to a camel also. Basically, you kind of have, it's not maybe the perfect analogy, but you kind of have an out of order belly over here. But to go into the scheduler, you need to go in order over here. And then when you finish, when you need to go out, when you're ready to go out as an instruction, you need to be reordered first. It's not the perfect analogy, but it helps you remember that an out of order machine has two humps here. And this is a general organization of an out of order processor from your book. I would recommend, not book, sorry, from the paper that I recommended. I would recommend reading it actually before next lecture. That would help you understand the next lecture a little bit better. That would enable you to see these different things. But you can see the humps kind of over here, basically. Decode, rename, and dispatch are in order. And then later you have these buffers that do out of order. And then there's a reorder and commit. That's the reorder buffer essentially over here. And this is Tomasulo's machine, which I'm not going to go into detail. Maybe we will talk about in a little bit more detail in the next lecture. But this is really enabled by register renaming, as we discussed. Essentially, I will finish very soon with the register renaming. Essentially, Tomasulo's algorithm to do out-of-order execution requires register renaming. That's why precise exceptions lecture was really, really important for you to understand, because that enables you to understand how you can map a register ID to a reorder buffer ID. But again, register renaming is more general. The register ID is renamed to the reservation station entry that will hold the register's value. You can do that also. You don't have to put it into the reorder buffer ID. And then you can keep the name anywhere, right? But I like the idea of reorder buffer ID for because it's reorder buffer ID. Reorder buffer essentially contains all decoded instructions, but not yet retired instructions. So it's actually a nice namespace, but that doesn't have to be true, as we will discuss toward the end of the next lecture. So a register ID is renamed to the reservation station ID. You can also think of architectural register ID being renamed to a physical register ID, as I discussed. And after renaming, you use the reservation station entry ID to refer to the register. And in the example that I'm going to show you next, in the next lecture first, we're going to use reservation station entry IDs, because initially we will assume we're not going to have a reorder buffer, because that will simplify the example. And then later we're going to add the reorder buffer. But again, renaming can be done to any arbitrary namespace as long as you're consistent about renaming. And the beauty is renaming eliminates anti and output dependencies. It approximates the performance effect of a large number of registers, even though ISA has a small number. So earlier, one of your colleagues asked the question, does reorder buffer actually improve performance? The way I described it in the precise exceptions part of the lecture, no. But the way you use the renaming to actually do instructions out of order and link dependent instructions to producer instructions and execute instructions out of order, it will help us improve performance, because it will get these anti-output dependencies completely out of the way through renaming. It will enable the linkage of instructions to linkage of the consumers to the producers, and it will enable us to execute things concurrently. So from that perspective, if you use the reorder buffer for renaming, yes, it will improve performance, but that's a benefit that comes from register renaming, if you will. And this is going to be what we're going to use, register rename table, but I've already shown you this in the picture that I drew, right? Now this is our register alias table. Registers can have valid bits. A register is valid if the value is trusted over here, meaning that the value is written into the register file, in which case the tag is not important. If there's an instruction that's going to write to a register that's in the machine that is not written to the register yet, that will set the value to 0, and this value will stay 0 as long as the register is not written. And the instruction that is decoded that's writing to register 0 sets this to 0, valid bit to 0, but it also sets a tag, basically renames the register 0 to a physical register ID, or a reorder buffer entry ID, or a reservation station entry ID, as we will see. And this will enable us to actually execute instructions and link instructions together. Okay, so this is probably a good place to stop. I will keep these slides for you. Actually, maybe let me cover the Tomasulo's algorithm very quickly, because the rest will be just the example over here. In the next lecture, I will start with Tomasulo's algorithm again. But basically, the way it operates is, if the reservation station is available before renaming, instruction and the renamed operands, source value and tag, are inserted into the reservation station. Basically, you only rename if reservation station is available. Otherwise, the machine stalls, basically. While the instructions in the reservation station, each instruction watches the common data bus for the tag of its sources. Remember, the tag is broadcast. If the tag is broadcast, tag is seen, the value is grabbed for the source and kept in the reservation station. When both operands are available, the instruction is ready to be dispatched. I'm basically reinforcing what I just discussed earlier from the perspective of what we're going to see. And you dispatch the instruction to the function unit when the instruction is ready, meaning both of its sources or whatever sources it may have, all of its sources are ready. And after the instruction finishes in the function unit, it arbitrates for this common data bus, or if there are multiple common data buses, it directly puts the tagged value, tag, onto the common data bus. And register file is also connected to the common data bus. And register contains a tag indicating the latest writer to the register, as we have discussed. That's the register renaming. If the tag in the register file matches the broadcast tag, you write the broadcast value into the register. This is how you update the register file, by setting the val bit also. Okay. And after that, you reclaim the rename tag, because there's no valid, to ensure that there's no valid copy of the tag in the system, because this tag is already broadcast, right? And you can recycle it at this point. And you can remove the instruction well, you don't remove the instructions from the reorder buffer at this point, but this is one reason you may actually want to associate a tag that's different from the reorder buffer entry, so that you can manage the tags in a different way. We will see all of this in the next lecture within the context of this exercise, if you will. Basically, we're going to simulate this machine that will execute these instructions, these 6 instructions. It's not a lot. And in your homework, you're going to see a lot of different examples of this also. And we're going to see how many cycles it will take to execute this in a non-pipeline machine, which is going to be easy. In an in-order dispatch pipeline machine with imprecise exceptions, no forwarding and full forwarding, which is going to be also easy. And then we're going to look at in an out-of-order dispatch pipeline machine with imprecise exceptions. Initially, we're going to assume imprecise exceptions. We're going to assume add takes 4 cycles, multiply takes 6 cycles. That's where out-of-order execution shines, actually, if you have long latencies. And we're going to see how much performance benefit out-of-order execution provides, while also learning how out-of-order execution exactly operates. Okay, so this is a great place to stop at this point. If there are any burning questions, we answered a lot of questions in this lecture. This was great, actually. Feel free to keep the questions coming in the later lectures also. It's good to be interactive. I see there's one burning question. How many memory accesses are handled? Is it now not possible to load something before it's written? So we're going to talk about memory accesses after we discuss the arithmetic instructions. Memory accesses are going to complicate things. Yes, so I think you're foreshadowing some of the issues that may happen with stores and loads. So for example, if you have a store instruction that's writing to an address that the load instruction is going to read from, that's going to complicate things. And we're going to see that load store handling is going to be important in an out-of-order execution machine. And we're going to look at methods for doing that. But that's a very good question. That's a little bit early in terms of what we're going to cover next. So first, let's deal with the arithmetic operations. But yes, loads and stores are going to pose the biggest problems. In fact, they're going to be the bottlenecks in an out-of-order machine, as we will see in the next lecture. Okay, very good question. I think I don't see any more questions, which means that I think this is a good place to stop. At this point, have a great weekend. Stay safe. And I will see you next week as we go through and simulate our first out-of-order machine. Take care.